All right. So here we're going to continue our conversation or discussion of enzymes. And so there we go. My screen's all shared. We are good to go. Um, we just were looking at the different classes, the different groups, the different types of enzymes. And when it comes to enzymes, we always have to look at uh, kind of the rules or the guidelines for enzyme nomenclature. So enzymes are always going to have a common name. For example, urease. Urease is the common name for the enzyme that catalyzes the hydrolysis of urea. Alcohol dehydrogenase catalyzes the oxidation of alcohols to their corresponding aldehydes. Now, some enzymes are going to develop an even more common name. Alcohol dehydrogenase is commonly known as ADH, but that's just kind of anecdotally, you might hear that. Now, a systematic name. There is a nomenclature system in which enzymes are named according to those six major classifications of those enzymatic reactions, including subclasses and sub-subclasses. Now, this classification or EC numbering scheme is what we also, or what we'll look at and what we were just kind of looking at. Each enzyme has a four-part classification number. So the numbers represent the class, so that one, our oxidoreductases, are the class. The second digit would be a subclass. The third digit would be the sub-subclass, and this last digit would be the individual serial number. So I always kind of think about this as you're starting very broadly. Your enzyme is an oxidoreductase, hence you have one. This oxidoreductase uses NAD plus and NADH as a cofactor. So then it's going to get a 1 or a 2 or some other number in that second digit. The key is that each one of these numbers tells you a little bit about the enzyme in question. And I'm going to bounce back just a tad to kind of show that. So if we think about, and this is kind of weird, just a second. Oh, gotta zoom out of this. Discard. Okay, sorry, that was funky. Um, okay, so here we go. If we look at these major classes of enzymes, what we've got is this 1.1, or actually, let me go up here, 1.1. This is an oxidoreductase, and since the second digit is a 1, it acts on CHOH group of a donor. Okay, good to know. This 1.1.1 is going to use either NAD or NADP as an acceptor. So what that means is that these enzymes, 1.1.1.5, 1.1.1.7, what they are all going to do, or both of these enzymes, since they have this one that is common, it's an oxidoreductase. The second one indicates that it acts on CHOH group of a donor. And then this third one is going to, well, it's going to be right here. It's going to use NAD or NADP as an acceptor. Now that's all information. Like, don't expect you to know specifics on, but it is good to, like, if you were to pursue the field of enzymology, these are all things that you would be very familiar with of your specific enzyme or related enzymes. So with that in mind, I can go ahead and switch my share. I don't think that you noticed anything there. Cofactors and coenzymes. I've used this term cofactor, redox cofactor, for example, whenever I was talking about NAD and NADP+. Cofactors and coenzymes. Oh, there are metal ions. These are going to act as cofactors. So that term cofactor is synonymous with metal ions, copper 2+, iron 3+, zinc 2+. Organic cofactors are generally referred to as coenzymes, NAD plus and coenzyme A. Now, there's a little bit one step further on this. I use the term redox cofactors whenever I'm dealing with something that is involved in an oxidation reduction reaction. So NAD plus If it's involved in oxidation reduction, it's a redox cofactor. If it's not, it's just a cofactor. Now, there are transient or tightly associated molecules or enzymes that tightly associate with enzymes. Co-substrates. These are coenzymes that are only transiently associated with the enzyme. There are prosthetic groups. These are coenzymes that are permanently associated with the enzyme. So one example of a prosthetic group that, well, in the case of heme, um, it was non-catalytic, but essentially there are enzymes that have molecules like heme that do something that give the enzyme the power to do something that it otherwise would not have. Now, there are many enzymes that are cofactor or coenzyme precursors. So if we look at this, this is a long list of different enzymes that are precursors. Um, I don't expect you to know these. I'm sorry. I don't expect you to know these cofact or these coenzymes, cofactors, these specifics, or anything like that. Really, what I want you to take away from this are these definitions. Coenzyme is an organic molecule. Cofactor is a metal ion. A co-substrate is transiently associated, whereas the prosthetic group is going to be more tightly associated. Now, coenzymes are going to be regenerated. Coenzymes are chemically challenged or changed in the reaction in which they participate. The coenzyme must be regenerated in order to complete the catalytic cycle. In the reactions catalyzed by lactate dehydrogenase, or LDH, NAD plus is reduced to NADH. NADH must be oxidized back to NAD plus to allow multiple cycles of the reaction to occur. Now, for transiently bound cofactors, sometimes the regeneration is accomplished by another enzyme. This is kind of an interesting idea. It's almost like you have E1 and E2. These are two enzymes, and maybe what E1 is going to do is it's going to take NAD plus and it's going to make NADH. Okay. Well, then what E2 is going to do, this is like a part of the same complex. What it's going to do is it's going to take the resulting NADH and convert it back to NAD plus. So it's going to keep the system kind of afloat, keep the system moving. Now, in the case of prosthetic groups, the regeneration occurs in a separate phase of the same enzymatic reaction sequence. Now, when we study enzymes, we study kinetics and we study catalysis. Kinetics is concerned with the timing, the pacing, the rate, the speed. How fast does a reaction occur? So the kinetic question is is this happening on the femtosecond scale? Is this happening on a nanosecond scale? That's a kinetics question. Now, in what sequence do bonds break and do they form? Do changes occur sequentially or simultaneously? Catalysis, on the other hand, is concerned with structural changes that occur during a reaction. Now, how are the bonds made or broken? What kind of intermediates are formed? What kinds of interactions occur between the enzyme and substrates, products, and intermediates? What is the nature of the enzymatic transition state? These are all of the big questions for when we're studying enzyme from a kinetics and a catalytic standpoint. So both or all of these things help us kind of illustrate what is an enzyme doing and how can you control it if you can control it at all. Enzymes differ from chemical catalysts in several ways. So when you think about a catalyst, one thing about a catalyst that's important is that like if you think about an organic catalyst, it speeds up a reaction, but it doesn't disrupt the equilibrium. Sorry, I'm yawning. Now, when you think about that, a catalyst is going to enhance the rate of reaction, and it's not going to be consumed. It's used in small amounts. What a enzyme is going to enable, and what's fantastic about an enzyme is that it allows a reaction to go even faster. So if you think about a catalyst as something that, speeds up a reaction, well, an enzyme does it even better and even faster. And there we go. In addition to that, we have much more mild reaction conditions. We have greater reaction specificity, and we have the capacity for regulation. So, firstly, whenever I think about reaction rates and higher reaction rates, I think of, well, we're going faster with a biological catalyst with an enzyme than an inorganic catalyst or an organic catalyst for that matter. We have milder reaction conditions. Now, there's an example that I always think about, and I mean, I always think of this. Uh, well, doesn't matter. Um, when you think about milder reaction conditions, what that means is that you've got to have this reaction that's going at, well, you know, room temperature. A reaction is being done at a very high rate and it's not generating a lot of like excess heat. It's not under an extreme pH or anything like that. We've also got this greater reaction specificity. So, you know, specific stereoisomers are produced. And then capacity for regulation. You have basically a mechanism to turn off a process or speed or turn on a process. Now, in terms of reaction rates, let's look at this table down here. Here we've got a couple of different enzymes on the far left. We've got carbonic anhydrase. That's a reaction. That's an enzyme that takes CO2, H2O, and makes H2CO3. Cool. And it does so under like spontaneous conditions when CO2 and H2O are taking place are reacted together. You're going to have approximately 0.13 of these reactions take place in 1 second. Okay. So in about 10 seconds, you'll complete this reaction one time. Awesome. Now in an enzyme catalyzed reaction, this is going to take place. That's 1 to the 10 to the 6. So 1, 2, 4, 5, 6. Okay, so that's going to be approximately 1,000,000 times per second. So your enzyme catalyzed reaction puts you at a considerable advantage. In addition to that, what we also have, let me erase that. We have an even greater extreme. We've got this enzyme known as staphylococcal nuclease. Now, this is an enzyme that sees nucleic acids, DNA, and RNA and just breaks them down into nucleotides. Now, in the absence of an enzyme, this is going to take place. And this is one of those things that I always like to do. I like to write out the number. I've got a total of, let's see, 12 zeros. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This many times per second. So we're talking for this reaction to be completed one time, it's going to be a long time. It's going to be billions of seconds. I think that would be about right. Meanwhile, with the enzyme present, staphylococcal nuclease taking DNA to RNA, or taking DNA and RNA down to individual nucleotides, it's going to be done 95 times per second. Now, this number and this number, they're worth recognizing as being considerably different from one another, but they're catalyzing different reactions. And that's kind of an apples to oranges comparison. What we want to do is we want to compare the non-enzyme catalyzed reaction to the enzyme catalyzed reaction. And we get a rate enhancement of 5.6 times 10 to the 14th. So it's that much faster than without the enzyme present. Now, enzymatic and uncatalyzed reactions. Some reactions are so slow in the absence of an enzyme catalyst that their half-lives begin to approach the age of the Earth itself. Enzymes can accelerate reactions as much as 10 to the 17th over the uncatalyzed rates. Urease, We've got a catalyzed rate enhancement of 1 times 10 to the 14th, an enzyme known as OMP decarboxylase, which is an enzyme that's involved in nucleotide degradation. You're going to see an increase in rate of 1.4 times 10 to the 17th. Now, how are enzymes capable of this? That is a great question. Well, we have a little bit of an idea of it if we go back to look at this right here. The ways that enzymes are so fast is because they can do all these things. Well, they can control the sequence that bonds break in. They've evolved to be able to do this at a very high rate. So now, free energy is ultimately going to predict the spontaneity of a reaction. The farther the reaction is from equilibrium, the greater the work. Free energy is related to the concentration of the products and the reactants and the intrinsic equilibrium constant for the reaction. Enzymes do not change the free energy. Enzymes accelerate the rate of the reaction. Now, here what we have is a free energy diagram that shows our ground state of our substrate and then the ground state of our product. In order to get from S to P, we had to go through this transition state right here. This transition state is denoted by a double dagger symbol there. Now, a stable reactant must surmount a free energy barrier to be converted to a product. Effectively, what this means is that that substrate has to go up the roller coaster tracks to meet the transition state in order to go down to your product. Okay. Now, the transition state is a species whose reacting bonds are midway to being formed or broken. So the transition state right here, that's where we're kind of between our bonds being made and our bonds being broken. We have a free energy, or delta G naught. A biochemist's free energy is the free energy of the reaction, but the forward and reverse reactions have a ground state. The transition state represents the point of highest free energy for a reaction step. Delta G double dagger is the free energy of the activation. So this delta G double dagger is basically going from our substrate to our transition state. That's the amount of energy that we require to get there. Now, if we go in the opposite direction, we still have to surmount that and go through that transition state. Our delta G double dagger is going to be greater if our reaction is going in reverse. Now, the transition state, from a thermodynamic perspective, the rate of the reaction is proportional to e to the negative delta G double dagger over RT. The greater the value of delta G double dagger, the slower the reaction rate because the fewer molecules have the sufficient thermal energy to achieve the transition state free energy. The greater the value of T, the faster the reaction. Now, when we look at a chemical reaction, we'll have a reaction that might take several steps. So in a reaction that has 2 steps, there are going to be 2 transition states. And what that means is that there are 2 activation barriers. The shape of the transition diagram reflects the relative rates of 2 steps. So the step with the highest transition state free energy is said to be the rate determining step, or the rate limiting step. Here's an example of a 2-step reaction where we have our 2 steps represented by A double dagger and I double dagger. Those are our 2 intermediates, this and this respectively. Now, these 2 lines, sorry, I'm going to bounce back and forth a little bit. These 2 lines represent our catalyzed and uncatalyzed steps. Now, looking at this from the perspective of a single step or a single intermediate, an enzyme acts by lowering that transition state free energy for the reaction being catalyzed. So it's going to take that double dagger, that transition state, and basically make it easier to get to it. So the effectiveness of an enzyme can be measured with these delta G double dagger. So if delta G double dagger is the free energy change that's required to get to your transition state, then delta delta G double dagger is the change of the free energy required to get to that activation set. Now, how is an enzyme going to lower that transition state? That's the question. It's okay, cool. An enzyme makes it more efficient, it makes it easier, but how? How is it going to do that? Well, by covalent, non-covalent interactions between the enzyme and substrates and products. So enzymes are biological catalysts, and the efficiency of a catalyst is determined by the difference between the values of delta G double dagger for the uncatalyzed and delta G for the catalyzed reaction. This is our rate enhancement, and a catalyst is going to lower the activation barrier by the same amount for both the forward and reverse reactions. So the forward reaction gets easier, the reverse reaction also gets easier. Now, these are all sorts of things that we talked about a little bit with respect to the tenfold rate enhancement only requires so the perspective or the change of the free energy of that transition state in order for this to become 10 times easier. So for that reaction to become 10 times easier, more favorable, we need a change in free energy of approximately 5.7 kilojoules per mole. Okay, that alone might seem like, oh, that's very interesting trivial knowledge. Thank you so much for sharing. I will remember that, and I will bring that up at my next, I don't know, cocktail party or box social or anything of that nature. But here's where it comes into play. A typical hydrogen bond is 20 to 30 kilojoules per mole. So that's the strength of a hydrogen bond. What this means is that a simple interaction in the transition state yields a tremendous rate enhancement. So if you can get, effectively what this means is that if the transition state can, I guess, be induced to make a hydrogen bond, there's enough energy, make or break a hydrogen bond for that matter, there's enough energy there to see this sort of rate enhancement. Because if you're harnessing 20 to 30 kilojoules per mole, that's effectively going to be a change of almost 6 kilojoules per mole, which is what we see here. So if a hydrogen bond can be established or broken and that energy can be harnessed, then you can see that rate enhancement. You can actually see it even higher than that. So when it comes to substrate binding, that's really where we get into the question and the feasibility of how much does a enzyme expedite a reaction. So a substrate is typically, and just so you're familiar, substrate is our language that we use or our term that we use that's analogous or it's similar to a ligand. A substrate is a small molecule and it binds to a large molecule through a bunch of weak forces. So a bunch of hydrophobic interactions or induced dipoles or hydrogen bonds. Now, your enzyme is going to be that large thing that the substrate binds to. A substrate binding site generally is a cleft or an indentation on the surface of the enzyme that is complementary to the substrate. So here what we have is a model for that. So this is a picture that's a little bit tricky. It's almost like a who is it? MC Escher, or yeah, MC Escher painting where it's like you look at it from one angle and it distorts your perspective. So what this is showing is here is our free substrate. Then this is our ES complex, our enzyme substrate complex. Our substrate and our enzyme are interacting with one another. What we have here are these brown blocks or the brown circles, which are indicating hydrophobic regions, hydrophobic amino acids. These hydrophobic amino acids on our substrate, or sorry, these hydrophobic regions on our substrate complement hydrophobic regions of our enzyme. Now this right here, NH to O, that would be where a hydrogen bond can be established. plus and minus is where we're going to have an ionic interaction or electrostatic interaction, some more hydrophobic interactions, and then hydrogen bonds. So these are all our non-covalent interactions. Now, that's one factor. Another factor is the shape. A complementary shape between our enzyme and our substrate is going to help this ES complex form. Electronic complementarity is also going to be at play. If we can have positive charges aligned with negative charges, we're going to have some electronic interaction between them. Now, enzyme specificity. Substrate specificity drives release of free energy. The number of substrates. So if we have a very, very specific enzyme, we might only have one substrate. Whereas there are some enzymes, for instance, hexokinase, which is an enzyme that's capable of actually seeing, any hexose. So it can bind to any 6-carbon sugar. Now, when it comes to terminology for number of substrates, there's absolute specificity. This is a type of specificity where an enzyme is going to catalyze the reaction of one very unique substrate to a particular product. Relative specificity, where we're going to catalyze the reaction of structurally related substrates to give structurally related products. The structure of those substrates is important. Stereospecificity catalyzes a reaction in which one stereoisomer is reacted or formed in presence of all others that might be reacted or formed. Geometric specificity, selectivity in regards to the chemical groups on those substrates. So knowing these definitions and these terms is going to be valuable. The examples, I don't need you to worry about those, but I want you to know the differences between our different types of specificity. So absolute specificity, one unique substrate to one unique product. Relative specificity, the reaction of structurally related substrates to give related products. So you can imagine that that would be, 2 or more different substrates, but similar substrates. Stereospecificity catalyzes a reaction in which one stereoisomer is reacted or formed in preference to all others that might be reacted or formed. Selectivity in regards to the chemical groups is going to be your geometric specificity. Now, this terminology, this is what's known as Cleland notation. E stands for enzyme, S is our substrate, enzyme substrate complex. We have a reaction take place where we have now an enzyme product complex, then our free enzyme and our free product are released on the other side of that reaction. ES and EP are transient complexes of the enzyme with the substrate and the product. The binding of substrates releases free energy, which can be used to overcome transition barriers. So here is one display of how that could work, where we have these lower free energy enzyme substrate and lower free energy enzyme product complexes. Substrate binding allows for entropy reduction. Substrates are oriented in the optimum way for chemistry to occur. Desolvation of substrates, where we basically have an aqueous environment that dissolves our substrate. Formation of weak interactions. In transition state offset formations of weak interactions in the transition state offset energy required to distort substrate. Weak interactions between the enzyme and substrate result in the enzyme making conformational or shape changes. Now, here's one thing that I always like to look at when it comes to speeding up a reaction and thinking about entropy of a reaction. So here what we have, it's a little bit tricky to kind of visualize here, but this is example A, example B, and example C. All right, so what we're going to see here is our reaction sped up based on the organization of our reactants. So we have this molecule, that reacts with this molecule. Okay. Now, I like to think about this in terms of these two reactants forming this product. And then I like to look at it from the angle of what is the likelihood that these two reactants come together in the specific way that they need to form this product. And, it's pretty good. I guess I'm just going to say it's pretty good because, if you have a high enough concentration, molecule A and molecule B, they're going to be bouncing around and they'll collide and they'll make our product. Now, if we look down at reactant or reaction B, okay, so what we have is this molecule where we've got some similarities. We've got these two carbons, these two carbonyl carbons, just like here and here. But these two carbonyl carbons, well, they have a bond or they have bonds between them. So they're this portion of our ring that's already in place. And so the likelihood that a reaction is going to take place where these atoms come together to close this ring off, pretty good. I would say that the likelihood of this reaction B taking place over reaction A is considerably higher because we just don't have that many other options. And then in reaction C, we've got the same thing where we're wanting these groups to close this ring off to make something like that. The likelihood that that happens is even higher than that of B. So our rate enhancement is higher because we just don't have that many other options. Now, desolvation is where our substrate and our enzyme basically they're going to interact with water because they basically have to, because we're in an aqueous environment. But what we're going to see is these hydrophobic regions between our substrate and our enzyme, they're going to be driven together. And the reason that they're driven together is because we know that the hydrophobic effect likes to take groups that are hydrophobic and get them together. And if there's any way that we can do that, that's going to be a favorable reaction. Now, when it comes to understanding the transition state, I like to take a look at this figure right here. And I think that this is a simple model where we have reactant going to product. We have a metal stick that we're breaking in half. If you leave that metal stick at room temperature, just in the atmosphere, the chances that it's going to be broken in half, it'll happen eventually. It might take 1,000,000 years, but it'll happen eventually. And in order to get from that straight metal stick to the broken stick, we have to go through this transition state right here, our bent stick. So when we are going from this substrate to this product, well, the question is, what's the likelihood that that's going to happen? Without an enzyme or without any sort of outside interference, it's not extremely likely. It will, but it will take a long time. Now, what we want and what we theorize is that our enzyme has a shape on it that's complementary to the transition state. Because if this enzyme floats around and has a active site that perfectly matches the substrate, well, it's going to bind onto that substrate. It's just going to hold on to it indefinitely. It's going to hold on to it unless, some other part of the enzyme gets manipulated. Whereas if this substrate or if this enzyme rolls in and it's kind of like this, well, then it can't bind to that substrate unless that substrate gives, unless that substrate undergoes some sort of change. So this theory and this idea is that there's a transition state of our enzyme that complements our substrate. Now, that's where we're going to wrap enzymes for day 1. We'll pick this up a little bit later, but I hope you have a good one. And